Hey, what's up? So this is the first video we're going to shoot after the starting of this class. What I'm going to do is I'm going to try to release 2 to 4 videos a week. I want to go over on that, but the problem is I'm also in school and I have to balance studying for that as well as this class. But I promise I will get 2 to 4 videos out a week, and also I will be responding to people in the Facebook group. What we're going to discuss in this video is logarithmic time. So what we're going to do is we're going to look at the patterns we need to see in these questions we get, in these interview questions, that indicate it's going to be a solution, the most optimal solution would run in logarithmic time. We're also going to just discuss logarithmic time in general and where you can find it. What I'm doing with these videos is I'm showing you the common classes of time complexities. You won't always see these complexities, but they're very common. You'll see them when you're trying to bound certain polynomials, certain common algorithms. You're going to see these bounds pop up, but in reality, in the real world, you'll actually calculate the exact operations, make an exact bound of sorts, and it could look a lot messier than these common bounds I'm showing you. First off, let's start with what is a logarithm. What is a logarithm? It looks like this. So whenever we are presented a logarithm, it's actually asking us a question. And what that question is what should I power the base by to get the number in this parentheses? It's almost the reverse of putting a number to a certain power. We're going in the opposite direction and seeing what power do I need to power the base by in order to get that inside number. So often we see the bare log sign, but in reality there's always a base here. Sometimes it's assumed, sometimes it's not. A more specific notation used in computer science is LG and then the parentheses, which means we're dealing with a logarithm of base 2. So let's be more specific and put a 2 there. So what this is asking us is it's saying 2 to the what is going to give me 8. How many times do I have to multiply 2 to give me 8? So it would look like this. So here we see that we have to multiply 2 3 times to get 8. But I want to reverse this. I want to give you a real more intuitive way of understanding this. Is what this is really saying is how many times can I have or cut 8 in half before I begin to reach a fractional amount. So if we cut 8 in half, let's see what that looks like. Here we see that we have 8, 4, 2, 1. What we did was cut in half, cut in half, cut in half. Our base is 2, so the answer to our logarithm is how many times could I cut that number in half before causing a fractional amount. So this is just an intuitive way. I don't know if this is mathematically rigorously true, but this is an intuitive way of saying we can cut 8 in half at maximum 3 times. And notice I said maximum. This brings me back to why this is a bounding and often used in our upper bounds. When we say big O of log n, we're interested in the maximum amount of logarithmic work we do. And in this case, the maximum amount of logarithmic work that can happen is 3 cutting in halves. What we need to do is we can draw another parallel. This parallel brings us to other algorithms like binary searches, going downwards in a heap, as we'll see later. These connections can be drawn to other algorithms. I just want you to understand the intuitive fundamental basis behind what a logarithm is. What we need to do is we need to bring back the original logarithm. So again, if we have base 2, we're saying how many times can I have 8? How many times can I cut it in half? And if we put a 3, we're intuitively saying, how many times can I cut 8 in thirds? How many times can I cut it in thirds? So when we see this under another base, like 3, we're talking about thirding our 8. If we have 4, we're talking about fourthing it. So if we go back to the 2, we're just having it. So this is just the original 2. We need to see why this matters, and we need to draw more connections here. Whenever we talk about these logarithms, let me erase this, we're always concerned with the behavior. As with anything asymptotic, any asymptotic measure, since we're upper bounding asymptotically, we only care about how this performs on the tail end. And at that point, only behaviors matter when n becomes arbitrarily large. So if we have 2 exact derivations of an algorithm's comparisons or certain operations like so, this is what these polynomials look like before we put upper bound on them. Before we worry about asymptotic matters, we just look what are the exact amount of operations. And so when you're looking at your time complexities, you're going to see how many for loops does this run? How many recursive calls does this have? And once you gather that exact information, you figure out what does this really behave like in the tail end? What is this really doing? What is the shape of the graph? So if someone were to ask you the asymptotic behavior of these two functions, what you would see is that they behave very similarly. I'm going to graph this online, put a picture right here, and these are what the two graphs look like. On the top, you see graph number 1, I think it'll be top, and the second polynomial, the log base 8, is going to be a little shallower. But what you notice is that both of these graphs have that same curving behavior. They curve and start to flatten at the tail end. And this is characteristic of logarithmic behavior. This is characteristic of an algorithm that is doing halvings, thirdings, eighthings, fourthings, cutting things in a certain set constant. And that's what logarithmic time will look like. So when we do bound this just becomes big O of log n. So these two polynomials are bounded by the exact same family of upper bounds. It's a family of functions and behaviors. This is the bounding, this is the exact. And now let's look at this in a concrete example and see how knowledge of this time complexity, knowledge of this class of time complexities can apply to bringing us to an optimal answer to a question. So let's look at that question right now. We are given a linear data structure, which is just an array in this case, not a linked list, not any other thing, just an array, a plain array. And it looks like this. So the array looks like that. And notice that this array is sorted. So I've said this in other videos, but whenever you get a sorted array, it's almost always going to have some sort of binary search. Most of the time in questions, there's never anything just given away for free. Almost everything has relevance to solving the problem optimally. We either will save work through iterations, maybe something is already obvious within the structure and we don't need to cache some space. There's multiple things that can save us time. And because this array is sorted, we're going to take advantage of that later. What you have to do is find the first occurrence of k as fast as you can in the best time complexity. And if you cannot find k, return -1. If you do find the first occurrence of k, then return the index. So in this case, if k were 3, we would return index 2. So that number right there is the first occurrence of k. So whenever we see binary search, I've seen other examples of people creating templates for binary search, people creating patterns. The key with any searching problem, whether it's binary search or anything else, is at every decision point or junction, you need to deeply consider how much of the search space can I absolutely eliminate by something very obvious. It's never obvious at first, but it becomes very obvious when we focus on that key decision point. And you'll see what I mean later when we optimize our approach. What we can do here is, to solve this, we can literally just find the first item, do a linear scan, look at -10, -2, 3. But the issue is, what if that 3 is all the way at the end of the array? Then we're going to have to touch n items. We're going to do a constant amount of work. Remember, constant time. Read operations into an array are constant. So n and then constant time per item, that's linear time. We can do better than linear time here because the array is sorted. There must be something that we can improve on. And you would vocalize this. You'd say, I don't know what the answer is, but I know that this can be improved because the array is sorted. There's something else we can do. So instead of doing a linear scan, which has a very bad worst case of searching the whole array, well, not very bad, but linear time, we can actually improve by doing an initial binary search. If we find k, then we go backwards in a linear scan. This isn't as bad. This is actually better in terms of wall time because we're going to do binary search like so. So let's do it right now. The bounds of our search are 0 and 7. So let's set those. So the bounds of our search are 0 and 7. We have 7 plus 0, which is 7, divided by 2, which is 3.5, truncate the 0.5, and we have 3. So index 3 is our midpoint. So we see that 3 is k. We see we have a match. And now what we would do is iterate backwards because we know this whole section is going to be k. And we iterate backwards until we find our answer. The problem with this solution is, at worst, what can happen is this. We could have the 3 be half of the array. And so as soon as we enter our binary search, we find k. And we're going to go n over 2 iterations backwards, or I think roughly n over 2. And what we're going to do is, again, a worst case of linear time. N over 2 is the same thing as 1 over 2 times n. Remove the 1 over 2, and we have linear time. We need to improve this. So we need to go back to the drawing board. Let's restore our array. So now let's rewind to the insight we made before. We know that every decision point is crucial. So if we're trying to execute a binary search, if we do a linear scan, we instantly put ourselves in a worst case scenario possibility, and we have a linear time upper bound. We have to keep it to cutting the search space in half. So how we can do this is let's return to our first instance of finding the item. So k equals 3, 3. At this point in time, there are a certain set of understandings that we are sitting at, and they follow like so. We know we are sitting at k. K can only be two things. This item is either the first occurrence of k, or it is a later occurrence of k. It cannot be greater than k because we're sitting at k, and there's no other possibility besides these two scenarios. We don't know anything behind this item because we can't do a scan, but we know this item and everything behind us is okay. So what we need to do is take record of this item. Say, this is a candidate. This is a candidate for being the farthest left, k. But we shouldn't stop. We might be able to find another earlier item. So we can continue our binary search. We can continue by saying 0 plus 3 is 3 divided by 2 is 1, or 1.5, and then we truncate the 0.5 is 1, and then we arrive here. So now we're at -2. It's less than k. We can't go left. We have to go right. So our search space diminishes to this. Now our search space just has a single item. So at this point, although we have found the answer, which we can see it's the answer, we still might find an earlier instance. So we go left, and our search space becomes this. And we see that we have nowhere else to search. Our right boundary is going to overarch our left boundary. Ultimately, we're going to be expressing all of the halves. We started like this, we started like that, and then we said, hey, check this item, it's k, but is it the first k? So then we go all the way back, our search space becomes this. Now the guy we were sitting at is out of the running. We've already said, hey, this is a candidate. We cache it somewhere in the frame of the call, in the frame of the current function call. And now our search space is indexed 0, 1, and 2. And then the middle of these is that guy. We see he's less than k, so then we go right. And then we see, hey, we have a match. And then we say, maybe this isn't the first occurrence, so we go left again. And at that point, our search space is exhausted. What we see here is, in the initial thinking of this idea, we immediately saw that this array is sorted. It's possibly logarithmic time in a solution. And then we figured out that we can just find the element with a binary search because we know the array is sorted, and then iterate backwards. But then there's a problem with that with linear time. And then we knew if we stay to binary search and fundamentally understand how our search space gets cut, and how if I'm sitting at k, I know that any item to the right of me can either be the item I am. If I'm sitting here, to my right, there could be more 3s. Or they're going to be greater than 3, they're definitely not k. So that caused us to go left. If we implement this iteratively, then we're going to be using big O of log n time. Our graph is going to look logarithmic, and our space is going to be constant. We're not creating any auxiliary structures that are keeping track of a size that can scale with the input of the array. If n becomes 1,000,000, the size usage does not change, it stays constant. That is that quick problem. I know it was an easy one, but I just wanted to throw that out there so that you can see where log n time complexities manifest. Other places that the logarithmic time complexity can manifest is when we're dealing with heaps, because we're going to have roughly log n levels, an upper bound of log n levels in a binary tree structure. We're going to have a upper bounding of log n levels in a binary heap structure, which a binary heap looks like this. And if we have 3 levels, we have 1, 2, 3, 4, 5, 6, 7 nodes. And if we have 3 levels, 2 to the 3 is 8. So 8 nodes bounds the 7 nodes in that full binary tree or binary heap. If it has the ordering property, it bounds that. If we were to insert an item or remove an item and we need to bubble items down, how many levels down can they go? it is logarithmic in work. Because if I know there's 7 nodes, I know I can just take the logarithm base 2 of that and know that at maximum, I'm going to go up or down roughly 3 levels, or 2 swaps. So in this video, what we got an intuitive understanding is of what a logarithm is and what it fundamentally asks us. We also saw one of the manifestations of logarithmic time in an example question, which the problem related to binary search, and we saw how that influences the way we are searching. Instead of doing the linear scan, we knew we could use logarithmic time, binary search. We saw how we could adapt our binary search to not just be a regular one, where we stop as soon as we find the item and return. We saw that we sit at the item and we consider, what does the position we're sitting at really mean? If we're sitting at K, fundamentally, to the right, it's either there's more Ks or there's greater items. So nothing to my right can be a candidate for the first occurrence of K. So we saw how we can make that distinction. And finally, we skimmed over how we can see logarithmic time when we're dealing with binary heaps, and how we have an upper bounding of logarithmic work when we're bubbling an item up or down. And that's covered in other videos, like the heap sort video I have, and it's something we're definitely going to get more practice in and look at more in depth. So in the next video, we are going to be discussing a very common time bounding called linear time, which is just O of n. It's very common. So that's what we're going to address next.